Well, good morning, and let's see how, let's try to see how photoelectric effect looks like if I didn't break it. So use your multitasking skills, read the question and think about it and try to answer it. And at the same time, let's try to look at experiments if they will work, because humidity kills static electricity. So what I have here is a piece of fur, plastic rod. All right, seems working so far. What I need to do is just charge it. This plate is made of zinc. How do I know? I can read. But I need to clean it up, because dirt, even slight, tiny, thin layer of it, would greatly increase the work function for the electrons. So it has to be as clean as possible. So only energy required to leave this plate would be the work function of the zinc plate. Every time, so, okay. To check the quality, I have to look at it. When I look happy, it's good. Okay. Now, let's see if we can charge it. All right, pretty good. Now we need a light. Nothing. As expected. This is just a visible spectrum, not energetic enough. We need a different light. We need something like this. This is a ultraviolet UV lamp. Let's see if this will work, hopefully. Let's see. Okay, if it's glowing, that means UV light is on. The whole charge disappeared. What happened? Well, highly energetic photons were colliding with electrons on this plate, and electrons had energy enough to leave this plate, be ejected. However, of course, now we have manufactured many materials which are more sensitive, like this one. Just an example of a photocell, solar panel. And now even regular light is energetic enough to generate electric current. So one of the really important applications of a photoelectric effect, solar panels. Now let's see what you said about this. Well, as you know, most of the time, even questions might be right, answers might be right or wrong. They're never bad. Yes, we'll see. So, the law says, well, actually, that's the law. It says this has to be positive, that's it. So we need to figure out the photon energy. This is a complicated equation. We have derived a much easier one. Yeah? 1240 over wavelength if it's measured in nanometers. And that gives us 1240 over 310, which is 4 electron volts. And 4 minus 3 equals 1. Positive, yeah. The photon energy is greater than the work function of binding energy in this situation. So, by the way, we also have found immediately the maximum kinetic energy of those electrons, yeah, 1 electron volt. This is what it is, kinetic energy maximum. No. Kinetic energy can be found using standard expression. We don't talk about relativity effects, and we actually can use this expression to calculate speed of those electrons, because 1 electron volt in joules is 1.6 times 10 to the negative 19 joules. And now we can use joules and kilograms to calculate speed in meters per second. Speed will be equal to 2 times 1.6 times 10 to the negative 19 divided by, that's an electron, so we should use the mass on electron, and we need to take a square root of that. I know it's supposed to be about 2 times 1.6, 3.2. 3.2 divided by 9 is 3 point something. I mean 0.3 something, 0.36. 36 is close. (31 minus 19). And actually it's easier. And 31 minus 19 minus 2. So it's about 6, and 31 minus 21, 10/5 meters per second. Well, you have a calculator, and I know the answer is on the next slide, so I don't have to work hard. Yeah, I was right. So this is how a photoelectric effect works, and of course we need to do at least more example, a regular problem, and this is one of many possible problems. We know the work function, and et cetera, et cetera, et cetera. So let's just do it. Work function naturally is given in electron volts. And we know that it is equal to the critical minimum energy a photon needs to have in order to start ejecting electrons. And we know this should be equal to that factor 1240 electron volt times nanometer over wavelength in nanometers, and that means critical. So if we want to calculate the critical wavelength, we just need to do this, right? 1240 divided by 4.5, 275.6 if we use this shortcut, the result is automatically nanometers. We remember that. And this is not in a visible spectrum because visible is between about 400 and 700. So this is shorter, which means higher frequencies, maybe ultraviolet or something like that. And frequency, what would be the frequency? Well, there are different ways to do that, but my personal preferred is that using this equation. Frequency will be equal to speed of light divided by the wavelength. But now we just have to add that coefficient factor of -9, and calculate it. So you use your calculator, I use my calculator, 3 10 to the 8 divided by 275, 10 to the -9. About 1.1, 10 to the 15th, okay. Now, this is that critical frequency. Below that, there will be no electrons ejected of that plate. But above, this is the new frequency, which is greater than the critical one. If it shines, well, what's going to happen? Electrons exist outside and actually travel. So, again, there are different ways to do that. What I can do, can calculate the wavelength of this new light, which should be equal to speed of light divided by 1.5 times 10 to the 15th. Three to the eighth divided by 1.5 15th. I got 0.0000002. That's meters. I don't want meters, right? I want nanometers. So what do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 200 nanometers. So this wavelength is shorter by about 75.6 nanometers. Now we can calculate that energy each photon carries with it, 1240 over 200. So 12 over 2, 6, right? 6 to 0. No, 6.2. Electron volts. And that has to be equal to work function plus maximum kinetic energy, which is 4.5 plus kinetic energy. So kinetic energy will be equal to 6.2 minus 4.5. What is it, 1.7? Electron volts. The last question about the retarding potential, which would prevent electrons from reaching the opposite electrode. And we know what is happening, basically. We have, well, there's that filament coating with that material, and electrons being ejected and start traveling from cathode to anode. But if we start attracting them back by electric field does work. Magnitude of this work should be equal to kinetic energy, And that should be equal to charge times voltage. That when that critical voltage is reached, electrons cannot travel through that potential difference. And of course, we could have used joules, but we know that in electron volts, if they travel this voltage, they should acquire that energy. So in electron volts, that voltage automatically is 1.7 volts. If we measure energy in electron volts. Of course, we could multiply by 1.6 times 10 to the negative 19th to convert in joules, and then divide by 1.6 times 10 to the negative 19th to convert to divide by the charge E, dividing by the charge E. And, well, that's it. So, oh, I have an extra slide, I didn't use it. So, the frequency, the wavelength, the energy, also in joules, the stopping potential, although this is outdated slide for the potential. Here, capital U is used instead of delta V. And the shortcut, which I used, so everything is in here. And that completes everything related to the photoelectric effect. So, of course, at the same time, when physics was developing new theory of quantum world, natural question was, what is the structure of atom? And Lord Thomson, he discovered electron. He got a Nobel Prize for that. So he had his own model, Thomson Model, so-called pudding model, represent an atom as a positive cloud with electrons sitting inside, because the atom has to be neutral. It has to be made of a positive charge and a negative charge. So the model would give us certain predictions here. Charges could easily travel through. And here, bigger picture. When particles travel through an atom, according to this model, they wouldn't be practically deflected at all. It's like shooting through the cloud. But there was an experiment, probably you know from chemistry, the Rutherford experiment, with alpha particles traveling through a thin film of gold. And the experiment would show that particles actually sometimes would be bounced back, deflected practically at 180 degrees. And the Thomson's model couldn't explain that. And the Bohr model was offered when electrons would be orbiting a very small but very heavy nucleus. The problem with that model that, as we know, when charge has acceleration, it should, again, See what's happening? It should be attracted, lose energy, and eventually collide with the nucleus, and atoms should cease to exist. All atoms should cease to exist. We wouldn't exist, nothing would exist. It would take like a fraction of a second for all atoms to explode. And, well, let's take a look so I could switch back. The Bohr, based on certain consideration and basically just being a genius, he said that atoms don't explode because they don't want to, basically. Electrons just orbiting the nucleus forever until something starts acting on them. But he was able to set a specific condition, mathematical condition for that, and that gave birth to quantum theory. So the Bohr models actually, again, is very simple by current mathematical view. Again, I studied it in 10th grade. And based on this model, every atom looks like this. We actually saw this picture 4 weeks ago when we talked about charges. And there's a solid, well, heavy nucleus in the middle of the atom. Electrons kind of wiggle around. Of course, that's just a model. In reality, we couldn't see anything like that happening. In reality, situation much more complicated. But this model is simple enough and good enough to explain lots of experiments. A neutral atom, as we know, should have the exact value for positive and negative charge, and the positive charge is represented by the periodic table. So Bohr said, well, let's treat atom like planets orbiting the sun. And the simplest situation, of course, single electron orbiting single nucleus, a positive charge, a negative charge. Simple trajectory is circular, and my question is, what do we know about circular motion? Everything. So this part is complete review, nothing new. mv squared over r should be equal to that force, which is Coulomb's force. Well, if they have the same, well, the electron has a negative charge, the proton, the nucleus, has a positive charge. So because we calculated magnitudes, that's our equation, Newton's law. And what can we extract? What kind of information? Well, for example, again, speed. Well, this is what I want to do first. mv squared should be equal to constant charge squared divided by 1 radius. Because I canceled r here and r there, right? Why do I need this? Because mv squared over 2 gives me what? Kinetic energy. But if we remember from the past, an expression for potential energy for two charges, k q1 q2 over r, tells us in this specific case it will be equal to same constant, one charge, second charge, potential energy maybe positive, maybe negative, maybe even zero. In this situation, it is negative because we're multiplying a positive charge and a negative charge. A negative energy means they attract each other.
Why did you put the 2 under that?
Because I want, and I do everything I want to. I want to have an expression for kinetic energy. I made by my own hands an expression for kinetic energy. That's it. So for this system, kinetic energy will be equal to Coulomb's constant, elementary charge squared, divided by the radius of the trajectory. However, now if I look at my expression for potential energy, I see it is very similar. Same Coulomb's constant, same elementary charge squared divided by the same radius. So I don't really need these expressions. All I need is a relationship between these two energies. Now I forgot it too. Yeah. Kinetic energy, which is mv squared over 2, equals this. So how can I write an expression which relates kinetic energy and potential energy? 2 times kinetic energy will be equal to -1 times potential energy, because that will give, well, this is whatever. That will give the exactly same combination of variables. Why do I need it? Because eventually I want to calculate the total energy of the atom. And total energy, as we know, is equal to what? It equals to kinetic energy plus potential energy. So, kinetic energy is equal to -1/2 of potential. So -1/2 of potential plus potential, 1 minus a half, which actually also makes it negative. See, U, actual energy, is negative. If we divide it by 2, we get a negative number. This is, again, a sign of a bound system. Then energy is negative. That means we have to do some positive work to take it apart. Well, also we can rewrite this expression in terms of kinetic energy. -1 times kinetic energy. Or actually we can flip those equations. Potential energy will be equal to 2 times total energy. Kinetic energy will be equal to -1 times total energy. So these are very important relationships. Of course, we could do more. For example, and we did it before, we can calculate speed. Yeah, speed. So for example, what speed will be equal to? Speed will be equal to, well, square root of constant charge squared divided by mass divided by the radius, etc., etc. Lots of algebra can be done. Period. Yeah. Linear momentum. What is a linear momentum? P. That's mass times speed. So anything we want to. But again, the problem is that in this theory, atom couldn't exist longer than a fraction of a second. Because that spinning electron would lose energy in form of electromagnetic wave, losing energy, falling down on the nucleus, exploding. So to save the theory, clearly the world exists. We see it. We feel it. So the theory is wrong. And, well, the idea was actually kind of simple. The example was already there, light. Light was particle, no, then wave, no, again particle, both, something more complicated. So now people started thinking, well, maybe particles are also not just particles. Maybe actual particles, electrons, protons, etc., also have some wave properties. And turns out they do. How can we differentiate between particles and waves? Diffraction. So, well, this is a classical experiment. warming up. And here you should see rings. First ring, second ring. Let's see if this will help. Oops. Where is it? Not really. Okay. The resolution of this camera is not very sensitive, but if you will decide, wrong button, if you will decide tomorrow and on Thursday to go to a lab, you would see this with your own eyes. Diffraction pattern. And those are electrons because we can use the left-hand rule and figure out that magnet deflects them. So electrons, turns out, behave like particles. Oops, don't want to be shocked. This is a description of another classical experiment. If you shoot electrons through diffraction grating one by one, every electron hits the photoplate at a certain place as a particle. But if you hit more and more and more and more and more places, you can start seeing the interference pattern. Maximum, minimum, maximum, minimum. And now we can just take a ruler, measure the distance, and calculate the wavelength. That's it, like we did for light. Turns out that wavelength is related to, well, MV, linear momentum of those electrons. The faster they travel, the shorter the wavelength is. This is same Planck's constant. And this expression has been offered first by Louis de Broglie. And, well, not Max Planck, Bohr, Niels Bohr, he used this approach to make one additional statement about atom. He said, well, if electrons are waves, they only can exist when that wave is a standing wave. Not just any regular wave, but a standing wave. Circular standing wave. What do we know about standing waves? Everything. That's it. So he added one additional expression. The circumference, well, that trajectory of electron should fit fixed number of electron wavelength, one wavelength, or two, or three. Only those trajectories are stable and exist. And now, if we're adding these two expressions, the de Broglie equation for the wavelength and the Bohr equation for standing waves, what is happening? Every single classical solution will have that number n inside it. Yeah? The radius r equals n times wherever. So that goes here, that goes there, that goes there, that goes there, which means now not any possible energy is, well, can be observed, or momentum, or speed, or radius, but only certain ones, given by the values of n equals 1, or n equals 2, or n equals 3, or n equals 4. And the symbol algebra tells us, yes?
Is the P that you're writing for the wavelength, is that linear momentum?
Yeah. But, okay. Yes, that is a linear momentum. We don't need to know these expressions. Just, you know, there's only one expression which is really important for us, for total energy. Turns out total energy is inversely proportional to that number squared with the fixed coefficient. And since we know the value of pi, Coulomb's constant, the mass of the electron, charge of the electron, Planck's constant, we can calculate this coefficient. And in joules, it's a very weird number, but in electron volts, it's negative 13.6. That's it. So it turns out the hydrogen atom can have only specific energies. The lowest energy for n equals 1 is negative 13.6 electron volts. Then we can calculate energy for n equals 2. Well, 2 squared is 4. 13.6 over 4. Negative 3.4. That's the next possible energy. We call them energy levels or just levels. We say it's kind of slang. Electron sits on that level. Yeah. An electron sits on a second level. That means the atom has energy of negative 3.4 electron volts. An electron can jump down, which means atom might lose some energy. An electron kind of getting closer to the nucleus. Yes?
So total energy we're talking about is the total energy of the atom and not the electron?
That's a language question. It's the energy of atom, which is the energy of an electron attracted to a proton, which is the energy of electron. Spinning proton, people say different things. They all mean the same. That's a system composed of two charges. One assumed to be heavy, so it's not moving, like the sun. Second is orbiting about. So proton technically has no kinetic energy if it's not moving. And if you want to calculate total energy, that's kinetic energy of the proton, which is 0, kinetic energy of the electron, which is wherever it is, and potential energy of the interaction. That gives the total energy. Well, so this is actually a very common situation in quantum world. Not any values are possible, but only certain. And the majority actually is restricted. Anything between negative 13.6 and negative 3.4 is restricted. Can't happen, ever. And not just energy, yes?
Why is the energy negative?
The simple answer, because we multiply the negative number and a positive number. A proton has a positive charge, an electron has a negative charge. If you calculate the energy, you have to multiply positive number and a negative number. That gives you a negative number. Then you adding smaller positive, the result is negative. What it means is that this system is stable. It exists on its own. We don't have to keep it together. Those parts attract each other. And if we want to break it, we have to do some positive work on it. So, let's calculate energies for the ground state. This word ground state has a specific meaning. It means n equals 1. Yeah. Ground state. It's grounded. We don't know why, for what, bad behavior. So the total energy for the ground state will be equal to negative 13.6 over 1 squared electron volts. That's it. Very simple. Now, what about kinetic energy and potential energy? Of course, we can go back to all that mathematics we just had done before. Where is it? Where is it? Where is it? Where is it? Here. But we can just remember that. Get kinetic energy, multiply by negative 1. Want to get potential energy, multiply by 2. That's it. Negative 1, well, that's for the ground state. Negative 1 times energy, number 1, 13.6 electron volts positive. It's kinetic energy, has to be positive. 2 times ground state energy. So negative 27.2 electron volts. And of course, we could do it for any other state, for any other level. And of course, for the sake of the exercise, we could go back to these equations and calculate the radius of the nth orbit. The smallest radius is a known number, and then just multiply by n squared. Well, the theory is kind of really simple nowadays. Question. Actually, 2 questions to you right now, because they're related, depending on how you answer question number 3. No, it's not 3 anymore. It cannot be 3 anymore. Is it? All right. So I had only 1 question before. Okay. So depending on how you answer question 3, you will answer question 4. So in a second state, energy, total energy, is equal to, well, you can see the pattern to choose your answer. If it's negative 13.6 over 1, choose 1. If it's negative 13.6 over 2, choose 2. Yeah. Our pattern recognition machine, our brain, tells you what to choose if you think it will be negative 13.6 over 3 or 4 or 5 or 6. So that's the first step. Second step, what does ionization mean? You should know that from chemistry. To ionize an atom, what does it mean? It means we have to take an electron and technically move it away infinitely far. It's like escape velocity for a satellite. Here, it's escape energy for an electron. What amount of work should be done to take that electron, which is in the second state, on the second level, and move it infinitely away? So, for the energy, what did you choose? What did you choose? What did you choose? Yeah. 4, because it has to be squared. That's the only thing to keep in mind. So, correct. Now, we just write an equation. Yeah. The energy, number n equals negative 13.6 over n squared. Plug it in, negative 13.6 over 4 electron volts. And if I read it, 1, 2, 3, 4, that's going to be negative 0.85 electron volts. Of course, you could just found it. Now, if you look at the picture, the highest level is 0, which is natural because all lower levels are negative. So we have to bring an atom from negative energy to 0 energy. After that, electrons just flies away. How much energy should we use? Well, this amount of energy. The work we need to done will be equal to 0 minus 0.85, which is 0.85, which is, as we know, 13.6 over 4. So again, same answer, number 4. That's what ionization means. And actually, if the atom, hydrogen atom, is in the ground state, to ionize it, we would have to spend 13.6 electron volts to take it apart. Well, I'll just a note. Here, ionization, this word means taking an electron away from an atom. Here, it also means taking an electron away. But there is some difference because in metals, in conductors, electrons not bound tightly to the nucleus, so it's much easier to take it out for a conductor. If we had a solid hydrogen, so the work function would be higher than this number. We would have to spend 13.6 electron volts just to take an electron off atom. Then we would have to bring it to the surface. But if we have a conductor, work function 4 electron volts, 5 electron volts. Question number 5. Let's say we shoot a photon with a given energy. It travels and encounters the hydrogen atom in the ground state. So those states also are called excited states, ground state, excited state. This atom is not excited, it's grounded. If you ground it, you're not excited. So, and a photon travels by, well, as we know, a photon and electron could collide. What do you think would happen in this situation? If a photon collides with an electron, that electron can absorb that energy and change the energy. And because it's all about energy, we would have to calculate what would be that energy. So the final energy should be equal to the initial energy plus the energy supplied by the photon. If the atom initially is in the ground state, that's the initial energy, and the photon carries 10 electron volts, negative 13.6 plus 10 gives negative 3.6 electron volts. So starting from this energy level, an electron should go to here. No, it should go here. This is negative 13. Oh, no, actually not here. Here, this is below negative 3.6 electron volts. Could it reach the level, the next level? No, it couldn't. In this region, energy region, all energies are restricted. Restricted area. There is a sign. Photon reads restricted area and moves away. That's it. Only specific energy a photon should have in order to excite an electron. And those specific energies for a photon must be equal to, well, depending on how it changes, the difference between two energy levels, like energy level M and energy level N. Only in this situation, atom can absorb or release a photon. So this event is impossible. Now, this is an example when it could happen. So a photon, well, disappeared means was absorbed. And in this situation, the energy transition happened from the ground state to the third state. How do we know? We can read. So the initial energy was negative 13.6 over 1. And the final energy, well, actually, it's the third one, negative 13.6 over 3 squared. So now the photon carried energy, which is equal to negative 13.6 over 3 squared minus final minus initial. This is what I'm writing. This minus is this minus, but there is another minus from the energy, minus 13.6 over 1. So wherever it is, it is, what is it, 9. 9. So 13.6 times 8 over 9 plus plus minus 9, 9, 9 minus 1, 8, 13.6. $12.29 minus plus, yes. It's a relatively simple algebra. Wavelength, I forgot to calculate the wavelength. Well, we know how to do that, 1240 over energy. And if we want to do the frequency, would be speed of light divided by wavelength. That, for me, is the fastest way to do it. So, oops. Again, 3 times 10 to the 8th over 102.5, but now we need to use 10 to the negative 9. That will be hertz. So the Bohr model explained experiments with different spectra of different gases. At the time, physicists could make vacuum tubes and tubes filled with gases, very, you know, just practically pure helium or pure, well, helium was later pure hydrogen, pure argon, and pure neon, and then excite with electricity, like with light. I held it, and then look at it, look at the spectrum, and turns out that spectrum actually had lines, and they couldn't explain why different materials would have different spectrum lines. But Bohr model actually gave an idea for that explanation, because first we can excite an atom by just colliding. Heating up means giving kinetic energy. Atoms start traveling fast, collide. So kinetic energy getting transferred into internal energy of atoms. Electrons gain some energy, but they cannot stay forever in excited state. Eventually, that energy is being released in the form of photons. And the energy of each photon can have only energy equal to the difference of two numbers provided by the Bohr's model. So in this situation, an electron is in a second state, and it, slang, drops, energy decreases. Calculate the wavelength. Well, that's a very simple problem again. Now, the initial state is negative 13.6 over 2 squared, but the final state is negative 13.6 electron volts. And now the photon energy will be equal to different number, yeah. So, well, basically 13.6 over 4. 13.6 minus 13.6 over 4 times 4 over 4, 3 over 4 times 13.6. That's going to be electron volts again, 13.6 times 3 divided by 4, 10.2. And now the wavelength is 1240 over 10.2. Well, about 12.3, let's say, nanometers, right? Divided by 10, 12. Well, it's a very energetic light, of course not in the visible spectrum. Well, what did I miss? That's correct. Why do I get 12 here and is it same? Of course. I need to add something in my coffee. Like milk. So, that's what I used. And this is a spectrum of a pure gas. For the hydrogen, for the pure gas, we would see several lines. That's in a visible spectrum, but of course there are lines which beyond visible spectrum. To find those lines, we would have to use photocells. And people, different physicists, have been measuring wavelength of that spectrum, and they have names, and we need to know those names just because each name represents a specific final state. So this is an equation which tells us how to calculate the wavelength for the visible spectrum. It happens when the final state is the second state. But if the final state is the third, in that case, it's infrared. We cannot see it, but we can measure. If the final state is the first, that will be ultraviolet. And of course, first, they measured all those wavelengths, and they figure out that just by plugging different numbers in, they figure out this equation, how to calculate the wavelength. But they didn't know how to explain why do they have to use natural numbers for calculating those wavelengths? And only Bohr theory explained that. Basically, the Bohr theory gave the way to calculate this constant, Rydberg constant. That's it. And when the calculation of the Rydberg constant fit the experimental result, that convinced everybody, yes, the Bohr theory is correct. Now, please, if the atom, the hydrogen atom, is in the third state, how many different photons with different frequency, photons with different energy, photons with different wavelengths can that atom produce? That's the question. The answer is 1 or 2 or 3 or 4 or 5 or 6. And of course, the answer is in, well, how many different energy differences can we calculate? So if an electron is initially in the third state, we say an electron is on the third energy level. This is here. N equals 3. It's an excited state. So what can happen? Eventually, it will lose some energy. But how much? Well, that depends. For example, an electron can lose this amount of energy, and we can say drop or jump from the third level to the second. But the second level is excited. So electron cannot stay forever. So eventually, it should drop down to the ground state. That's another possible energy difference for electron, which is a photon energy. But also, an electron can jump directly from the third to the ground state. That gives the most energetic photon. Well, we call it 3 to 2, 1, 3, 1. But because there are no other energy levels existing, so that's the only what can happen, which means only one photon, second or third, can be emitted in this situation. 3. And in general, this theory works fine for any ion which has only one electron orbiting. So let's say we have a helium, take one electron off, leave one electron orbiting. In that case, we can use exactly the same equations. We just have to replace the charge of an electron with the charge of 2 electrons. Well, 2 protons, technically, 2 protons. Now, if we go deeper, look inside the nucleus, what do we see? We see that a nucleus also has a structure. It's composed of protons, many protons, if we have a heavy nucleus like uranium. And each proton has a positive charge, so they repel each other strongly. Without anything else, a nucleus couldn't exist, so there has to be something else. And those particles which keep them together, neutrons. So every nucleus has, well, except just natural hydrogen, which doesn't have neutrons, but every other nucleus has protons and neutrons. And from chemistry, you know that we can use a special symbol for every element. And, well, that's not the only actually notation. People use different sides and different levels. But this is an example. At the bottom, this number represents the number of protons. For a neutral atom, it's also the number of electrons. But if we count protons and neutrons together, that gives so-called atomic mass number. That's this. So this is the number of protons This is the number of protons and neutrons. Protons and neutrons together called nucleons. So A represents the number of nucleons. And again, don't forget that for a neutral atom, the number of electrons is equal to the number of protons, because the charge has to be equal to 0. And if you look in the periodic table, well, you can figure out properties of a nucleus. Now, please tell me, this is a very important isotope. What is an isotope? An isotope is an element which has the same number of protons but different number of neutrons. A stable isotope of carbon, carbon-12, has exactly 6 protons and exactly 6 neutrons. This is a radioactive isotope of carbon, carbon-14. It's being used for carbon dating. Some people believe in carbon dating, Republicans don't. It's easier than believe. Now, so the question is, in this particular isotope of carbon, how many neutrons do we have to count? Well, basically, this is a short memory test. Total number of nucleons is what? 14. Do you see how many protons does it have? No. What do? You go to the periodic table, you search for this symbol, you look at the number 6. That means this is a 6th element, not 5th, 6th element. And for the 6th element, it has 6 protons. (14 minus 6, 8). That's how it works. Now, of course, we could use international system of units to measure masses, energies, but numbers would be really, really weird, the negative 31st, negative 27. So, like we have invented a mole to measure number of particles in chemistry, here people have invented a different unit of mass, atomic mass unit. And this is the outdated symbol, just atomic mass unit, or people use just a little u. And by definition, atomic mass unit is equal to the 1/12 of the mass of an atom of carbon-12. So what do we need to do to measure atomic mass unit? We have to take one atom of carbon-12, put it on a scale, measure mass, and divide by 12. What is, we get in the result, that's what we call atomic mass unit. And this is the conversion factor between atomic mass unit and kilograms. And now if we use atomic mass units, all masses have kind of simple number. Now, you see that if we would round it up, the mass of a neutron and the mass of a proton would be the same, 1 and 1. We cannot do that. So every time when we have to use masses for calculating anything, and we have to use all the digits, all of them. Otherwise, the result will be not accurate enough. For the electron, which is about 2 times lighter than the proton, we still have to use all those digits. Question? This is a test if you can read that table, periodic table on the wall. If you can, the answer is what? 6. Because that's a carbon. If you can't, in that case, you should ask, where is it in the periodic table? That's it. So, for any isotope in a neutral state, of course, the number of electrons is equal to the number of protons. 2 questions. My goal today is to reach the limit of the Weber sign. What do you think? We know that we could use kilograms to measure masses, but now we have to get used to using atomic mass units. So, what do you think about the mass of one carbon-12 atom and the mass of the nucleus of that atom? If we use not international system of units, but atomic mass units. Now we need to remember a definition of atomic mass unit. Yeah, what is the definition of atomic mass unit?
1/12 carbon-12 atom.
Yes. So if one atomic mass unit is equal to 1/12 of the mass of carbon-12 atom, what will be the mass of a carbon-12 atom equal to? How do you know? You know multiplication table. 1 times 12 is 12. So this is just a definition of atomic mass unit used backwards. Yeah. 1 atomic mass unit is equal to the mass of carbon-12 atom divided by 12. So the mass of carbon-12 atom in atomic mass units will be equal to 1 times 12, 12. Nothing special. This is more interesting. Nucleus. What's going to happen? Well, an atom is a combination of a nucleus and electrons. In this situation, 1, 2, 3, 4, 5, 6. So if I want to get the mass of a nucleus of carbon-12 atom, what should I do? I should get the mass of carbon-12 atom and subtract what? Why not? No, they do contribute. They contribute a lot. This is how much they contribute. This number is the mass of a single electron. And if carbon has 6 of those, you have to subtract 6 masses of a single electron. So it will be less than the mass of a carbon-12 atom. This is a nuclear mass, the mass of a nucleus. This is the atomic mass, the mass of an atom. And these numbers not equal to each other. It's very important. Even if the difference is, will seem little, it's actually huge for atoms. So, atomic mass 12, the nuclear mass less than that. Now, energy. Well, this is a famous Einstein's equation. For any amount of energy, we can calculate how much, or for any amount of mass, we can calculate how much energy is stored in it. But actually, for any amount of energy, we can calculate how much mass would we need to store it. And mass actually bends space. Also, well, Einstein told us that's general theory of relativity. So energy bends space. And, well, one atomic unit. Well, first, of course, we have to use international system of units because we don't know where else what to do. If you want to calculate the amount of energy related to this mass, 1.66 times 10 to the negative 27 times speed of light, about, well, 2.99 times 10 to the 8 squared. This is a number we need to calculate. 1.66 10 negative 27 times, open the parentheses, 3, 10, 8, close parentheses, squared, equals. If my calculator doesn't lie to me, that's this number in joules. But we already know that joules is not very good unit to measure energy for tiny particles. So what do? Convert it first into electron volts. So what do? Continue. 1.4. You should check my calculation. 10 to the negative 10 joules. And 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So what do? 1.49 times 10 to the negative 19. Try to be more accurate over, ahead of myself, over 1.6 times 10 to the negative 19. Well, I subtracted 1.49. 10 negative 10 divided 1.6. I'm giving you time to do the same. That's why I'm doing it. Because I make mistake. You have to check my calculations. And now I forgot what I was doing. I will make mistake definitely. So 931250000 electron volts. Again, not very convenient number. How can we simplify this? Well, we can use the power of 10. 931 times 10 to the 6th electron volts. Or now we can use a standard representation of a million mega. So my calculation is not very accurate. It should be 0.5 about that. So this is how much energy is stored in one atomic mass unit if we use mega electron volts, millions of electron volts. This is just a conversion factor which we always can use if we want to calculate the energy stored in a certain amount of mass if that mass is measured in atomic mass units. We just have to multiply by the conversion factor of 931.5. 1 times 931.5. This is how much mega electron volts is stored in 1 atomic mass unit. Multiply this, multiply this, multiply this. So you see, actually, 0.5, a half. It's a large number in energy. So that's why we cannot neglect electrons. This is the summary. All basically conversion factors, that's it. Question. I'm getting closer to the limit of the Webb sign. As we said, because protons are positive and the distance between two protons is so small, it's very tiny, the Coulomb's force has to be huge. The Coulomb's force, you just calculate charge times charge divided by 10 to the negative 15 squared. That's going to be a huge force. So there has to be a different type of force which prevents protons from moving away from each other. What kind of a force? Gravity cannot be so strong. There is no friction, no magnetic force. They don't love each other. So it's a new force. It has to be a new force. And because that force is very, very strong, the official name of that force is strong force. Called strong nuclear force. That's it. That's an official name. That's the force between nucleons. The Standard Model explains the existence of that force using even smaller particles, quarks. And the Standard Model had to be confirmed very fairly recently by discovering the Higgs boson. So the Standard Model works, strong nuclear force exists, and basically the existence, the stability of an atom is based on the play between two forces: attraction due to strong nuclear force and repulsion due to strong Coulomb's force. Many atoms are stable. For example, carbon-12, iron. Some not stable. They will decay eventually, because when the size of the atom grows, eventually electric repulsion overcomes the attraction. But anyway, if something happens to the nucleus, mass changes because energy changes. When the nucleus is close to each other, nucleons close to each other, we have a nucleus. Well, we can put it on a scale, measure mass. That's going to be a certain number. What are we going to do to take it apart? We have to do some work. Take one, move away. Take second, proton, neutron, move away. If we do some work, that changes the amount of energy, that changes mass, because E equals mc squared. There is amount of energy which holds nucleons, binds them together. That energy has a name, binding energy. And if we do a work, the amount of which is equal to binding energy, all protons and neutrons now are apart from each other. And if we count the mass of each proton individually, if we count then the mass of each neutron individually and add them up, turns out individually the total mass of those particles will be greater than the mass of an actual nucleus made of those particles. There is difference. That difference is the binding energy, well, over c squared. So the difference in masses has a name, mass defect or mass deficit. People call it differently. And if we know the mass defect, multiply by c squared, that will give the binding energy. Of course, we just have to do some examples. But before, you should answer the last question for today. I believe that's the last question on WebAssign, number 12. Do you have it? But you don't have number 13, right? Oh, shoot. Okay, next time. Well, still, that will be the record anyway. So, let's do the record. This number, which you read in the periodic table, yeah, and you will have to use it to solve a couple of problems. So if you read the number 209, 65.38, what does it mean? Specifically here for iron. You read, what does it say? 55.845. And those are used atomic mass units. Atomic mass units. So, if we know what does this number mean, we can calculate binding energy and other things. If not, we will make a mistake. This is the periodic table of elements. For each element, an element, it's an atom. It has a nucleus and electrons. So it has to be, well, first of all, not nuclear. It's an atomic mass, well, average. So that number which we read is a combination of two. The nuclear mass plus the mass of all electrons around it. And if we need to calculate nuclear mass, we have to take that number and subtract mass of the electrons. Thank you. So now you can do many more problems. Much more homework can be done. And tomorrow, and my microphone died. Test. My microphone died.